In this video, we are going to talk about the remainder theorem and the factor theorem. First, let's see if we can determine a relationship between f of a and the remainder when f of x is divided by x minus a. We'll do an example to illustrate this relationship that we'll state for you shortly. Determine the remainder when x cubed plus 7x squared plus 2x minus 5 is divided by x plus 7. Well, we know from synthetic division that to figure out that remainder, what we could do is put a negative 7 out to the left because we're dividing by x plus 7. And then bring down the 1. Negative 7 times 1 would be negative 7. 7 minus 7 would be 0. Negative 7 times 0 is 0. 2 plus 0 is 2. Negative 7 times 2 is negative 14. Negative 5 plus negative 14 is negative 19. So we see from here that when we divide that cubic polynomial by x plus 7, the remainder is negative 19. Okay, now, given the same cubic polynomial, let's evaluate f at negative 7. Well, plugging in a negative 7 for x, we would get negative 343 plus 343 minus 14 minus 5. And we would see that f at negative 7 is equal to the remainder when f of x is divided by x plus 7. And what happens is that leads us to a rule which we call the remainder theorem, and here it is. When a polynomial f of x is divided by x minus a, the remainder is equal to f of a. If the remainder is 0, then x minus a is a factor of the polynomial. So what if we asked you to determine the remainder when 3x to the 4 plus 10x cubed minus 8x squared plus 14x plus 5 is divided by x minus 9? Well, rather than do synthetic division, we can just plug an x value of 9 into the expression for f of x. We change the sign of that linear factor, so instead of plugging in negative 9, we plug in positive 9. And when we do that, we do some simple evaluations. We get 26,456. Well, since f of 9 equals 26,456, therefore the remainder when we divide f of x by x minus 9 is 26,456. Now, what if I give you a cubic polynomial with a couple of unknown coefficients, and I tell you that when we divide by x minus 1, the remainder is 1, and when we divide by x minus 3, the remainder is negative 35. We want to solve for a and b, so we want to get two equations. So, since the remainder when we divide by x minus 1 is 1, that means that f at 1 must equal 1. So let's evaluate f at 1. We get a times 1 cubed plus b times 1 squared minus 10 times 1 plus 4, and we end up with a plus b minus 6. Well, that means that 1 is equal to a plus b minus 6. And that allows us to isolate for a and get an expression, an equation that we'll call equation 1, a equals 7 minus b. All right, now let's look at the second sentence. Since the remainder when we divide by x minus 3 is negative 35, that means f at 3 equals 35. Well, plugging in 3 for x, we get the expression 27a plus 9b minus 30 plus 4. We know that must equal negative 35, so that means ultimately that 27a plus 9b equals negative 9. And we're going to be able to say that that is equation 2. And now we can use either elimination or substitution to solve. We're going to use substitution this time. We'll substitute equation 1 into equation 2. So in other words, instead of saying 27a plus 9b equals -9, we'll say 27 times 7 minus b plus 9b equals -9. And we distribute collect like terms and solve for b, and we see b is equal to 11. Well, from equation 1, we know that a is equal to 7 minus b, so that would mean that a is equal to -4. We were asked to solve for a and b, so that means a is -4 and b is 11. So in other words, that means that the polynomial function -4x cubed plus 11x squared minus 10x plus 4 has a remainder of 1 when divided by x minus 1 and has a remainder of -35 when divided by x minus 3. Now here's something interesting. We know that if the remainder is 0, then the divisor is a factor of the dividend. Okay? Well, we can use this to help us determine factors of expressions. We call this the factor theorem. Now this is a really big, important theorem in math. X minus a is a factor of f of x if and only if f of a equals 0. When we have a higher order polynomial that we wish to factor, greater than a quadratic, we can look for a value of x that makes the expression equal 0. Then we can use synthetic division or long division to determine the quotient. And we can continue to do this process until we've worked our expression down into a quadratic or another expression that's factorable. This is, to some extent, a trial and error process. We plug in potential values of x until we find a value that makes the expression equal to 0. But there are a couple of things that we can do to cut down our work in this trial and error process somewhat. If the lead coefficient is 1 and if f of a equals 0, in other words, if x equals a quote-unquote works in the factor theorem, plugging in an x value of a makes the expression equal 0, then that means that either a or negative a is a factor of the constant term in the expression for f of x. Okay, so what does that mean? Here we go. Again, remember, this will work if the lead coefficient is 1. Imagine that we have a polynomial function shown. The lead coefficient is 1, the coefficient in front of x cubed. Since that's the case, what we're going to do is we're going to focus our attention on the constant term of 15. And we're going to ask ourselves, what are factors of 15? And the answer is 1, 3, 5, and 15. And you might be tempted to say, sir, 1 is not considered a factor. For purposes of this discussion, let's say that it is. Now, since we have a lead coefficient of 1 and since we have a constant term of 15, the only values that might make the expression equal to 0 are 1, 3, 5, and 15, or -1, -3, -5, and -15. So what we'll do is in doing our trial and error process of looking for values that make the original expression equal 0, we're only going to look at these values. So what that means is, if you look right at the bottom of this slide, it means it would be a waste of time for us to try x equals 2 or x equals -2 or x equals 4 in the factor theorem process for this polynomial, because none of those are factors of 15. So let's do an example. Oh, sorry, and one more. What if the lead coefficient's not 1? Well, just to summarize it really quickly, let's take an example of this polynomial expression right here. If the lead coefficient isn't 1, like it isn't in this case, then what we're going to do is we're going to look at factors of the constant term, which are the constant term is -3, so we'll look at positive or negative factors of that. So they would be plus or minus 1, plus or minus 3. And then we'll also look at factors of the lead coefficient, which in this case is 2. So factors would be 1 and 2, and so we'll put a 1 and a 2 down here. And so what this means is the only values of x that might possibly make the polynomial 0 will be, now we're going to look at, let's focus on a potential denominator of 1 for right now. Well, we could say positive 1 over 1, or sorry, positive 1 over 1, or negative 1 over 1, or positive 3 over 1, or negative 3 over 1. Now let's look at the other denominator of 2. We might also try positive 1 over 2, or negative 1 over 2, or positive 3 over 2, or negative 3 over 2. In other words, the only values that might possibly work in the factor theorem to make the original expression equal 0 will be values where the numerator of the fraction is a factor of the constant term and the denominator of the fraction is a factor of the lead coefficient. Now, and then plus or minus. It could be positive or negative. Now, truthfully, in this course, we tend not to ask those questions on tests that require you to look at non-integer values of x that make the original expression equal 0. So typically speaking, on a test, you'll probably get a question where to determine the factor, you will use integer values of x and then do a synthetic division process until you get down to a quadratic, which is factorable. Let's do an example and you'll see what I mean. Let's fully factor the expression shown. Well, we know from our work in factoring that we always common factor first. So looking at the original expression, I see that we can common factor out 2x. So common factoring out 2x leaves us with an expression of 4x to the 4 minus 25x squared minus 30x minus 9. Well, let's try and factor that using the factor theorem. Now, recall from the previous slide that we are now looking at the expression 4x to the 4 minus 25x squared minus 30x minus 9. Well, let's focus on potential integer values of x that make this expression equal 0. And let's focus on factors of 9. So let's look at positive negative 1, positive negative 3, positive negative 9. Well, the easiest one to try is positive 1. So what we're going to do is focusing on this expression, we're going to let x equal 1. When we do that, we get a value of negative 60. This tells us, since f at 1 doesn't equal 0, that x minus 1 is not a factor. So we keep trial and erroring, we move to the next one. Let's try x equals negative 1. Well, when we try that, f at negative 1 equals 4 times negative 1 quantity to the 4 minus 25 times negative 1 quantity squared minus 30 times negative 1 minus 9. Ultimately, the answer is 0. This tells us that x plus 1 is a factor. So what we're going to do now is use synthetic division on that fourth degree polynomial as shown here. One thing worth noticing, there's no cubic term, there's no exponent, there's no term that had x cubed. So we put a 0 in there as a placeholder in the x cubed column when doing our synthetic division. Well, when doing our synthetic division, we ultimately get that x plus 1 is a factor, and so is 4x cubed minus 4x squared minus 21x minus 9. Okay, so not forgetting our original common factor of 2x, we've now factored our expression to that, but we still have that cubic factor in the middle, and let's see if we can break that down a bit more. Well, what we are going to do now is continue doing the factor theorem. We're not going to try an x value of 1 because we already tried that and it didn't work. Once a value doesn't work, it won't work for later factors either. What we're going to do is we're going to retry an x value of -1 because it's possible for an x value to work more than once. So now we're going to do the factor theorem on this cubic expression right there. Plugging an x value of -1 into that expression, we get 4. That means x plus 1 is not a factor of that cubic. Well, we've already seen that x equals 2 and x equals -2 won't make the expression 0. And the reason is, if you go back a while ago, we had we talked about how when you have a constant term of 9, you'll try plus or minus 1, plus or minus 3, and plus or minus 9 in the factor theorem. So we won't try x equals 2 or x equals -2. That would be a waste of our time. And we'll try x equals 3. Well, if we plug an x value of 3 into this cubic expression, we get 0. That means x minus 3 is a factor of the cubic expression. We'll use synthetic division now to determine what the other factor is. So using synthetic division, putting a 3 outside, which represents x minus 3, and putting the coefficients of the cubic here, we ultimately get 4x squared plus 8x plus 3. So that means 4x cubed minus 4x squared minus 21x minus 9 is equal to 4x squared plus 8x plus 3 times x minus 3. When you combine that with the earlier work, you get this original 5th degree polynomial has now been broken into 4 different factors. We might think we're done, but look at this quadratic expression right there. We've been talking about how to factor quadratics for some time now, so let's continue to try that. Factoring 4x squared plus 8x plus 3 gives us 2x plus 3 times 2x plus 1. So now we can say that this 5th degree polynomial is actually equal to 2x times 2x plus 3 times 2x plus 1 times x minus 3 times x plus 1. One final question, given that x plus 4 is a factor of 2x cubed plus px squared plus 42x plus 24, let's solve for p. And what we'll do is, since we know that x plus 4 is a factor, we know that f of -4 must equal 0. So we plug in -4 for x, and we let that equal 0. And then solving it out, p times -4 quantity squared is 16p. Moving, keeping the p term on the left and moving the other terms to the right, we get 16p equals 272, or in other words, p is equal to 17.